Okay, here we go. Here we go. So let's take a look. We left off yesterday. I don't know where that went, but we talked about lots of stuff. We talked about symmetry. We talked about, we're trying to fill in the sheet with the descriptions of all these parent graphs, right? So what we're developing here, we're putting together kind of a toolkit of parent graphs that we're going to use for the rest of the year, right? So we're going to be able to do transformations of all of these parent graphs. And the strategy is this. We want to be able to come up with, we want to know what the parent graphs look like. So let's get them clicked all the way close. We want to know what they look like, and so then we're going to be able to do the same kind of stuff to tweak any of these parent graphs in the same way. We'll be able to translate them around. We'll be able to stretch or compress them vertically, and we'll be able to reflect them vertically. Those are the things we're going to be able to do, right? Once we know what all the parent graphs look like, the process will be the same for all of them. Okay, so we left off yesterday, we went through, I think, the cubic function, right? And that's where we left off. So today, let's look at square roots and cube roots. Okay, so square root graph. Now, what do we know about a square root graph? So this is going to be, our function is going to be f of x equals square root of x. Okay, you probably already know you know a lot about square roots. You know more than you think you do. What types of numbers can I take a square root of? I get the perfect squares. They don't even have to be perfect squares. Like the square root of 2 is a legitimate number, right? They positive numbers, and there's one other possibility. You can take square roots of positive numbers or 0. Okay, right? We just can't take square roots of. We can take square roots of negative numbers, but we don't get real results, right? We get strange numbers that we'll talk about soon. But we're looking for real results here, right? We're graphing real functions, and so we're graphing functions in the xy plane, which implies we're graphing only the parts of the functions that involve real numbers. Okay. So then we'd say that we have to exclude all the negative numbers. So the domain of a square root function is the non-negative numbers. How would I say that? X is what? But not just positive.
Numbers greater than 0. Greater than or equal to 0.
Greater than or equal to 0. Okay, so x is greater than or equal to 0. Okay. Now let's graph a few key points on our function. If I evaluate my function at 0 to get the y value, well, what is the square root of 0? 0. Okay, so we know we've got a point here at 0, 0, right? I can't put in a negative number, but I could start to put in some positive numbers. What if I let x equal 1? What's y? 1. Square root of 1 is 1. So we're going to have a point up here at 1, 1. And what would be the next convenient point for us to use? Okay, if I put in 4 for x, I'm going to get what back for y? 2. Square root of 4 is 2. So we'd go over 4 and up 2. And that gives us the shape of a square root graph.
Wow.
It looks like that. Okay? Make sense? So it starts off pretty steep, and then it just kind of levels off with time. It always rises, though, forever. If I go far enough to the left, there's no y value I couldn't get to. So what's the range going to be?
All numbers greater than 0.
Greater than or equal to 0, right? All values greater than or equal to 0. What's the x-intercept?
0.
How about the y-intercept? What about the maximum number of roots? 1. Good. Maximum number of roots is 1. Okay? Oops. And so if we're solving a square root equation, which we'll eventually do, the maximum number of roots we can ever get is 1. Okay, we won't get to that for a while, but keep that in mind. End behavior. Okay, what about the limits here? As x approaches infinity, what does f of x approach? Infinity. Okay, can x approach negative infinity? No, it can't, right? So that one, in this case, there really isn't any left end behavior. You can just cross that out, right? They do it on here. Yeah. Okay. So there really isn't any left end. Well, we could do one thing on the left side. What is the left edge of this function? Zeros, right, 0, right? So as x approaches 0, y approaches 0. That's a little bit hokey. That's not really what we're getting at when we talk about end behavior. End behavior, we want to know what's going on at the extremes, right? So there really is no left end behavior, right? All we get is just an endpoint there, okay? Continuous or discontinuous? Continuous. I can put my pen down at 0, 0, and I never have to take it off the board to graph the entire function, right? Okay, so questions on that one. Does that make sense? Okay. All right. Do you want to do a test for symmetry on this too? See if you remember your test for symmetry.
Yeah,
Okay, you can see there's no symmetry. Let's show that though. See if you can remember. What's our test for even symmetry?
rotating or
No. Even symmetry,
You can fold it.
that's the folding symmetry. Line symmetry about the y-axis. Very good. And what's our test? F of negative x equals f of x. Okay, how do we remember that? Because these are hard. I know when we talked about it yesterday, everybody probably thought, okay, I think I got that, but it's easy to forget that relationship. So in math, I'm always harping on ways that you can reinforce this without having to memorize a fact, because you'll forget the fact, right? Here's a way to think about that. What's a good example of a function, a really easy one, that maybe we've already talked about, that has even symmetry? Say it again. Y equals x squared, okay? And that's even exponent, right? So it's a power function with an even exponent. And so if we were to graph this, we know what x squared looks like. That's a parabola, right? So it's going to do that kind of a thing. Well, think about some points that goes to. Let's pick some easy ones. Like, what if we go over 1 and up 1? If I go back 1, what do I do? I go up 1. So the coordinates are -1, 1, and 1, 1. Well, doesn't that fit that plan right there? Think of this the same. If I plug in a negative number, an opposite of x, I should get back the same y value as I get with f of x. Isn't that what that's saying? If I evaluate this, if x is 1, then f of -1 is just equal to f of 1. And that makes sense. Look, they have the same y value, don't they? Right? So there is no negative sign there, because whether the number is positive or negative with a parabola, the y coordinate is the same either way. It's positive. See my point? Okay, so that's a way you can remember that f of -x is equal to f of x. It's got the same y value as f of x does, because whether we go in the positive or negative direction, we get that folding symmetry. Okay, what was our test for odd functions? Of -x equals. Okay, and what was a good example of a function that had odd symmetry? X cubed is a good one, right? That's kind of the classic one we want to think of. So x cubed, remember, looked like this. Because this is the symmetry, this is rotational symmetry about the origin. So let's pick a couple easy points. Let's pick the point 1, 1. And then down here, if I go left 1, I go down 1, right? -1, -1. Well, what happens? If I put in the opposite of an x value, like the opposite of 1, I get the opposite of the y value. So they both became negative this time, which makes sense, doesn't it? If I go in the negative x direction, I'm going in the negative y direction also for this function. That gives me that rotational symmetry. Okay? So we can see we need the negative sign there because the y values are going to change. Okay? Easy way to remember it. So let's apply this to our square root graph and see what happens. If we do this test on a square root graph, let's see what happens when we evaluate it at -x. Got a problem, don't I? Right? If x is positive, -x is negative, and I can't plug a negative number into the square root function, and so it doesn't work. There's no symmetry there, is there? Right? And we don't have symmetry. If we go back, we can see there is no folding symmetry or rotational symmetry, is there? Okay? Good. Okay, what about a cube root? Let's look at a cube root. Cube root of x, okay? So let's plot a few points here, a few convenient points. What's the cube root of 0? 0. Okay, what's the cube root of 1? 1, right? And when we say cube root, think what we're asking. What's the cube root of 8? 2. How come?
Because 2 times 2 times 2.
Okay, because 2 cubed is 8, right? Good. So the cube root of 1 is 1 because 1 cubed is 1, right? So we're going to go through the point 1, 1. What would be the next convenient point? 8, 2, right? If we put in an 8, the cube root of 8 is 2, so I got to go clear over 1, 2, 3, 4, 5, 6, 7, 8. That one's going to be about right there. So on the right side,
But you can do negatives on this.
but I can do negatives. You're right.
Like the other one.
I can only not take even roots of negatives. I can take odd roots of negatives, and this is an odd root because 3 is odd, right? It's a cube root or a fifth root. Those are all examples of odd roots. So what is the cube root of negative 1? Negative 1. How come? Because negative 1 cubed is negative 1. Think about that. Negative 1 times negative 1 is 1. Times another negative 1 makes it negative 1 again, right? So we've got the point 1, 1. We have the point over here, 8, 2. Here we have the point negative 1, negative 1. And then what's another convenient point?
8, negative 8.
Negative 8. What's the cube root of negative 8?
Negative 2.
Negative 2. Okay, so we'll go back 6, 7, 8. We'll go down to there. What kind of symmetry does that appear to have?
It's like some
Yeah,
odd.
rotation.
Yeah, it's rotational, isn't it? Right? Okay. So we could test it real quick. So that's going to be the cube root of negative x. Okay, now this is some math that we'll review this later in the year, but see if we can make this proof now. There's a little bit of a, see, I don't know if how much of this you've done in Algebra 1. This might be reviewed, it might not. Maybe you've never seen this. There's a property of radicals, right? If I have, I don't know if you've ever even done any of this stuff. If I have like the nth root of a times b, or n could, if it's 2, it's a square root. If it's 3, it's a cube root. If it's 4, it's a fourth root, etc. What can I do with that? Any ideas?
Simplify.
So how can I rewrite that? There's a property here. Like if I had, for example, if I had the square root, you've done stuff like this without knowing it. If I had the square root of 2x, how could I rewrite that?
Square root of 2 times the root of x.
I could do that, right? I could split it into separate
So
square
it's just the
roots.
same thing, but with the variables.
Right, right. And you've done something like this before too. What if I had the square root of 50? How do you simplify that?
The square root of 2.
You'd write it as the square root of 25 times 2, right? Because we want to have a perfect square factor, which I would then write as the square root of 25 times the square root of 2. And what's the square root of 25?
5.
Okay. So without knowing it, you've actually used that property before, right?
Oh, I remember.
Okay, vaguely. And we'll review all this stuff again when we get to quadratics, simplifying radicals. Okay, but so we've got this property up here. It's the nth root of a times the nth root of b, right? So up here then, well, what's our a and what's our b? N is 3 here. What's being multiplied there? Negative 1 times x, right? So I could rewrite this as the cube root of negative 1 times the cube root of x, and what's the cube root of negative 1? Negative 1. So I get negative cube root of x. What do you know, right? That's the same thing as saying negative f of x, isn't it? So we just proved it. It's got odd symmetry, right? So we should expect it to have that kind of rotational symmetry that we saw. That one? Yeah, that one. Oh, wrong one. That one. So what's the domain then, looking at this graph? All reals, what's the range? All reals. X-intercept?
0.
0, 0. Y-intercept? Maximum number of roots? 1. End behavior. This time we do get end behavior on both sides. As x approaches infinity, y approaches infinity. It's going to go up forever, isn't it? As x approaches negative infinity, y approaches
Negative.
good. Continuous or discontinuous?
Continuous.
Yes, ma'am.
So why isn't it, three,
Yeah.
roots?
Okay, because how do I want to explain this? Well, part of it is you'll see later when we solve cube root equations. But there's another part of it. If I were to move this, no matter what I do to this function, there's no way that it's ever going to have more than one x-intercept at a time. There's no way the function could ever somehow twist around and go through the x-axis more than once. And so that's probably the easiest way to see it. The maximum number of x-intercepts it could ever have is 1. Whereas when we had the cubic function yesterday, with the cubic function, I was able to do this. Let's see. Right, I was able to take my cubic parent graph, and we'll talk much more about this later. This is all stuff that, I mean, we're kind of just paving the way for future discussions. But our basic parent graph for a cubic function looked like that. But I could tweak this thing to do something, for example, like that, where I could end up with 1, 2, 3 x-intercepts. I can't do that kind of thing for a cube root. I'm never going to be able to get more than 1 for a cube root. Okay, so for now, that's probably my best explanation. Later on, we'll be able to fill in the blanks more thoroughly.
Okay, thank you.
Okay, all right, so moving on then. We got the cube root. Now we'll move on to last 3, a reciprocal function. Reciprocal function, what do you think that is?
F of x equals f of 1 over x.
1 over x, that's it. Okay, 1 over x. Okay, so this one does some weird stuff. Now, can you tell me right now a value of x that I have to exclude from the domain? 0. 0, how come?
Because you can't divide by 0.
Can't divide by 0. Okay. Every other x value is fine, but I can't, there's nothing else up there that I couldn't do. But because I have an x on the bottom, my domain is x cannot equal 0. Everything else is fine, but that's one that we can't have. Okay, what's happening at 0 though? Let's see if we can get an idea here. We'll kind of think in terms of a t-table. If I pick some values of x, tell me what's going on. Like if I were to pick x equals 1, what's the y value? 1. Okay, so it goes through the point 1, 1. What if I pick the point 2?
Oh, I don't like this.
What's it going to do?
1 over 2.
1 over 2. So when x is 2, y is 1/2. So it's going to be like right there. When x is 1, 2, 3, 4, 5, what's y going to be?
1 over 5.
1 over 5. So what's it doing? It's just getting smaller and smaller as x approaches infinity. We're going way out there on this one. See if you can think about this. We'll talk a lot about this in calculus. As x approaches infinity, what would be happening to that fraction? The top is always going to be 1, but what's happening to the numbers on the bottom? They're getting huge. Now, what happens to fractions if the top stays fixed but the bottom gets big?
It goes.
Compare 1/10 to 1/100 to 1/1000 to 1/10,000. What's happening to those
It's
fractions?
getting teeny, teeny, teeny.
They're getting really small,
But it never reaches 0.
right? But it never quite reaches 0, but it's always approaching 0. So this is another example of that limit idea. Like, remember we talked about this, if I have my distance to the door every second for the rest of eternity, do I ever get to the door?
No.
No, but I'm always approaching the door, right?
Yeah.
Yes, sir.
Could you show us this in Desmos graphing calculator,
Yeah,
that example?
yeah, we'll look, you bet, we'll look at
Wait, so
this.
it looks like that, kind of?
It's like
It just with a little, like-
and it gets closer.
It's gonna be asymptotic on that x-axis, we'd say, right? It's gonna keep on, if we go to the right from this point, it's just gonna keep getting closer and closer and closer to the x-axis, but never quite get there, right? So that's what we'll call an well actually, yeah, we can add the asymptote right here. one asymptote is the x-axis, which is y equals 0.
Wait, what's an asymptote?
So an asymptote, remember, that we talked about that unit 1 a little bit. I can't remember which unit it was. Maybe unit 2, I can't remember. But that, you know, it was in the domain stuff, so that was beginning of unit 2, right? Where we had one function where we had an asymptote, it was this function, where there was an asymptote that showed up, where the function approached it but it never got to it, right? So that's what an asymptote means. An asymptote means a line that a function approaches but never gets to. That's the meaning of the word asymptote,
Oh, okay.
okay? So now we've kind of figured out what the ant's journey is going to look like when he walks to the right from the point 1, 1 along this function. What if he walks to the left? What if I put in a point like x equals 1/2? What's 1 over 1/2?
1 over 1/2 is
2. Okay, so if I go back the other direction, when x is 1/2, y is 2. What if x is 1/5? What's y?
What's it like?
1 over 1/5 would be
1 over
5, right? So when x
That
is
took too
1/5,
long.
y is 5. So what's it doing on the other side?
It's just going,
Same kind of thing with the x-axis, isn't it?
that's just
Right?
like a
That's all.
L almost,
So it's going to do this. It's going to continue on up like that.
or,
So it's asymptotic on the x-axis, which is y equals 0, and it's also asymptotic on the y-axis. What's the equation of the y-axis?
X. Or something. I got
X
really
equals
confused
0,
when you went
right.
like that. Well, I thought it was
Okay.
gonna go to 0.
Crazy, right? So there, we're asymptotic on both of those axes. Now let's look at the other side. Let's look at negative values. If x is -1,
It's just
what's y? 1 over -1 is -1. So we're right here. We're at this point.
That's rotation.
so is it rotation?
Okay. Yeah.
Cemetery?
Does that make sense? Because now what's going to happen is I get further to the left, as I go, you get large negative numbers. Like if I were to take something like -5, I'm going to get the point -1/5, aren't I? If I take the point -1,000,000, I'm going to get -1,000,000th, which is a very, very small negative number. So it's doing this, isn't it? Okay, what if I go towards x equals 0? Like if I pick the value x equals -1/2, 1 over -1/2 is -2, isn't it? Right, so I'll go back 1/2 and down 2. If I go -1/5, it's down at -5, and we can see the same behavior here, can't we?
Yes.
Right, so it's asymptotic on both the x and the y axes, okay?
Show the max.
Well, I guess let's finish this real quick. So the range is what then?
The range is R.
Is it?
Except for 0.
Except for 0. So the range is y cannot equal 0, right? Okay, the x-intercept,
There
None.
is no X in this section.
the y-intercept, the maximum number of roots or zeros? 1. Because if I slid this thing up or down, I could have
Oh, I thought
one
you could
x-intercept,
slide
but I
both.
can never have more than 1, right? That make sense? And once again, that one, I know that one probably doesn't feel like that might sound a little weird, but we'll get back to that stuff later. For now, just, hopefully that makes a little bit of sense, but that's just a fact we want to remember, is that this can only have one 0. End behavior, as x approaches infinity,
Y approaches 0.
0.
y approaches 0. As x approaches negative infinity, y approaches 0. Exactly. Okay? Continuous or discontinuous?
Continuous. Discontinuous.
How come it's
You
discontinuous?
gotta pick up your pen to draw full line.
Gotta pick up my pen
Or at
to
least-
draw the whole thing, don't I? Gotta take my pen off the board, so this is one that's discontinuous. Okay, let's do our test for symmetry real quick. We'll just do it right on here. If I wanna test symmetry here, what's it gonna be? We can tell by the graph.
F of negative. Wait, what?
Odd or even?
Odd.
It's gonna be odd, isn't it? And we can show that. F of negative x equals 1 over negative x. Well, what's 1 over negative x? What do I do with the negative there?
X. Wait, no, it's X.
Put it in front. Yeah, exactly. Positive over negative is negative. So that's equal to negative 1 over x. But negative 1 over x is just negative f of x. Right? So it's odd symmetry, which is what we saw. It's rotational symmetry about the origin. Right? Okay? Okay, what about an exponential function?
Wait, can you see the circle in the decimal calculator?
Yeah, oh yeah, yeah, let's do that. Right, so here's what it looks like. Okay, so here it is. If I do f of x equals 1 divided by x, that's it. Okay?
Can you zoom out a whole bunch?
Sure. Yeah, and if I zoom out, what's it do? It's just gonna,
It just looks like
That's
Yeah.
pretty cool.
Oh, you can't even see
Right.
it. I was like,
so
wait.
this is kind of an interesting thing to do. I want you to notice what happens, and this illustrates a point. So let me graph the asymptotes. Let me graph the lines x equals 0 and y equals 0. Okay, I'll make these both blue. Now, when I zoom way in, you can see that the function is very different than the asymptotes, right? But what do the asymptotes do? The asymptotes are just giving us, the horizontal asymptote especially, is just giving us the large scale behavior. So when I zoom really far out, what are you going to notice is going to happen?
They're gonna look like they're the same. but
They're going to
not.
look like, it's going to look like the asymptotes, isn't it? Right? So the asymptotes are useful in looking at large scale behavior. They don't really tell us what's going on right around, the origin, where usually we're interested in exploring things, right? But when you get way out there, they do a good job. Okay? Exponential function. Okay, so this is the function. We're only going to look at one type of exponential function. We're just going to look at the one, they use 2 to the x. We can do that, I guess. That's fine. So I'm going to give you 2 of them. An exponential function is just any function where I'm taking a constant to a power, right? That's what an exponential function means. This is different than a power function. A power function was like x squared or x cubed. What's the difference there?
It's the
Okay,
power.
good. The variable is the base, and the exponent is a constant. In an exponential function, the base is the constant, and the variable is the exponent. See the difference? And so this is an example. There's an infinite number of these that I could write. This is one of them. The one that we use the most, I'll make this green because it models natural phenomena. The one that we would use the most would be f of x equals e to the x. What's e?
Earth.
It's 3.
No. Do you know what e is?
It's an irrational.
It's an irrational number.
That
It's
equals
like
3.
pi. E is what we call the natural number. It's about 2.7128, something crazy like that. Okay, but it's, okay, we'll
Yeah,
pick
it's
this up,
3.
you'll get that.
But
Oh yeah, that's good.